Hi everybody, thanks for coming. So this is actually the second thesis competition which we are organizing. So last year it happened probably like 15th, so it's very close timeline. So so this is organized by IEEE Student Branch. So there is few of us from the Student Branch, that is me as a chair, and there is few others sitting around here who is part of the Student Branch of IEEE. So we are running the second time this year. So that's me giving some introduction. So we had it last year. It was very similar fashion as like this one, and that was the photo of the winner, and there's a news article in the School of Engineering website. So you could see that there was 7 speakers. We got improved this year. We got 9 speakers if Mohsen shows up. And there was 3 winners last year, and as usual there will be like a audience choice prize also this year. So at the end of the talk we will be asking the audience to rate the speaker, and there will be an audience choice too. And there was around 30 to 40 attendees just like this. So so the agenda is simple. So we have some introduction, and we have a bunch of lightning talks from the speakers, and probably if everyone sticks around we could take a picture, and then some pizzas, and so the judges is here, and that's me. So the thesis format is like every speaker would be having 3 minutes per speaker, and they would be just having 3 slides, and there will be some quick time for judges and audience to ask questions. So this is more of our addition to thesis, because in general thesis format there may be no audience questions, but we added that this time, and judges will select 2 winners and audience will vote the 3rd winner. That's how we plan to do it. So this is slightly modified version of classic 3-minute thesis. And we would like to thank School of Engineering and our Electrical Engineering for sponsoring the whole event to make this actually a thing. So we could get started, and there's a QR code. Probably we'll pop this at the end of the talk for you guys to write. Anyway, this was the pictures from last year. Again, I don't know, I made that, okay. Again, so this is the whole list of acknowledgements. So IEEE to organize the rebate scheme, and also department for hosting the event, school for communication photography, and the judges and you guys for coming and actually showing up to listen. So let's start with the talk, and the first talk is by Suhail actually. So Suhail is here. So he is talking about advancing drive cycle construction for electrical vehicle using advanced machine learning techniques and application in micro simulations. That's a long title. And probably do you want clicker, or you could use the keyboard, or you can use the clicker, up to you.
Clicker would be nice.
Okay, so this is the clicker, and so probably at the end of less than 30 seconds I will somehow give you some signals.
Okay, thank you.
All right, then I'll give the floor to Suhail.
Imagine a world where all cars are running through electricity, where air is cleaner and streets are very quiet. Sounds right, no? So that's the world we are working towards using electric vehicles. Like there is a little catch here, that these electric vehicles, even though they sound very eco-friendly and sustainable, but they lose around 1/3 of their electricity in the electricity conversion. And so we have introduced a new project Power Drive in 2022, where we are trying to remove these losses by 30%. If you consider the transportation sector itself, that contributes towards 1/4 of the total greenhouse gas emission. And in Europe, that's 3/4 of the cars are contributing to that 100% of the transportation emission. With introduction of these power drive project, we are trying to reduce the powertrain efficiency. We are trying to improve the powertrain efficiency of electric vehicle by 30% more. Now you must be wondering what a civil engineer is doing in electric vehicle technology. Like, we are like a detective of engineering world. What we are trying to do, whenever electric vehicles come up with a solution of more economical or more efficient powertrain modules, what we try to do, we try to simulate the real world scenarios into the simulation. So what we do, we create the speed versus time data that is known as drive cycles. These drive cycles we put in a simulator in a laboratory, which runs through a particular amount of time, which gives the long-term assessment of the modules that they are being generated. Now these drive cycles, they are like humans. They get old with time, with increasing in infrastructure and increasing the growth of vehicle on the road. They get absolute with time. So there are two main research questions. The first one is how to generate these drive cycles with their representativeness and the effectiveness properties. And the second one is how do these characteristic parameters affect global and local aspect of these drive cycles. So in order to mitigate these two or come up with these two gaps, I have derived like 4 main objective of my thesis. The first one is to prepare a systematic methodology for electric vehicles, to construct the drive cycles for electric vehicles. The second one is investigate the factors which influence the construction of drive cycles. If you see here, this is going to be the model, input model. If you put the local traffic parameters, these parameters for example, for Dublin city, you will get the drive cycle output as a Dublin for Dublin city. But if you put all of these characteristic parameters for the entire Europe region, you will get the drive cycle for the whole Europe region. That will have one more benefit, that you can integrate this model in a car following model or a micro simulation models. One of the example is like we have all electric road where cars are running on a road and they can be charged via induction on the roads. So these models will help to actually give the local drive cycles of electric vehicles to these kind of models where you can simulate either if you want to reduce the battery capacity of electric vehicle, so they can get charged over the time on the road. And the second part is to know the demand of power grid for each hour. That's it for today. Thank you.
Thanks. So do anyone have questions? Call for questions.
Thank you very much. I suppose I'm just curious on, are you simulating data only, or will you also be using real?
So one of the objective of my thesis is we have to integrate the model with car following model, in which we will be having codes which can simulate or integrate with the existing software which are capable of simulating these kind of simulations.
And is it possible to compare that model then to like real data?
Yes, that's the main part of it. So we have standard drive cycles from Horizon Europe, from Europe, that is known as new electric vehicle drive cycles. So we will be comparing our data with those existing drive cycles so that we have the comparison which one is doing better.
All right, let's thank the speaker once more.
Thank you.
So the next speaker is actually Brian. Oh yeah, he's here. I don't know, probably from internet. All right, the floor is for, do we have the timer ready? Yes, all right, good.
So my name is Brian and I'm a PhD student in the School of Physics in the Magnetism and Spintronics Research Group, and I need this. And so in order to try and summarize my research, I kind of have to introduce a couple of key concepts and then I'll have a little summary at the end. And the first one is something called the magnetization. So I don't know if you're familiar with a vector quantity, but if I ask you to picture a sort of a magnet, you're probably going to picture something like this. We have a bar magnet and a north pole and a south pole. And then you might even picture these kind of field lines. Instead, I want you to picture an arrow, okay? This arrow is the magnetization. So you can kind of define it in kind of layman's terms as the strength and direction in which something is magnetized. And these kind of magnetization arrows can do all sorts of funny things. And one thing we do is when you put it in a magnetic field, it'll actually experience a turning force or a torque, which causes it to align to the kind of direction of the field. And this should be kind of very familiar to you because this is exactly how compasses work, where the arrow is this magnetic material here, and then obviously the field is provided by the Earth. The second concept is a little bit more tricky. So it's called magnetoresistance, and it occurs in sort of layered magnetic materials, where you have a magnetic material, and then like a metallic spacer, like copper, and then another magnetic material. And depending on the orientation of these two layers, or these two magnetizations, you can get high and low resistance states. So if you have a parallel configuration, you can get a high resistance state, and if you have an anti-parallel configuration, you can get a low resistance state. Now, you can probably imagine that if we can control the configuration of these two, we can do all sorts of wonderful things. But what we're going to have to do is we're going to have to pin one layer, and then we can use a magnetic field to kind of rotate the other layer. And the way in which we pin things is actually what I research. It's called exchange bias. So it's possible to use another type of magnetic material called an antiferromagnet, so I've highlighted it in green here. And this provides a sort of like a coupling or a pinning. So you pin one layer, you pin one layer, and then that's kind of fixed in space. And then you apply your magnetic field and you can rotate the top layer. So then you can say, okay, I can either encode information based on if I have a higher or lower resistance state, or I can also use it to sense magnetic fields. But this exchange bias, this kind of pinning, this undergoes a couple of things that are problematic. And the first one is a sort of decoupling or a reduction in the strength of this coupling as you go to higher and higher temperatures. Now, if you want to incorporate that into something like a sensor, that's okay if you're having that kind of room temperature. But if you have it in a computer where you're storing information, that can become a problem. And the second thing we do is we want to replace the materials that are in them right now. So right now we use kind of precious metals, which are expensive, such as platinum and iridium. So we're looking for kind of precious metal-free alternatives. And that's it.
That's right under 3 minutes. So do people have any questions? First call, second call. Oh, yeah.
What are the use cases, applications of your work?
So, do you know sort of magnetic hard drives? The way you store information in bits? You basically have kind of little blocks of these, and you read it out as either a high or low resistance. So a low resistance could be a 0, and a high resistance could be a 1. So that's one application.
Storage.
Yeah.
All right, that's it. So thanks to Brian again. So next is from Ed. So Ed is here. So you have a clicker here if you want.
Just the button to click.
Just try it if you want. Yeah.
Very nice.
All right. And there's a pointer if you want. All right.
Okay. So I work in speech to text, so that's speech in, text out. Now in my field, we're very dominated by the big tech companies, Amazon, Meta, Google, Microsoft, who have lots of resources at their disposal, huge compute power, huge amounts of data, and they use that to create giant AI models, giant deep learning models that can cover huge amounts of domains, right? Like large language models, multimodal models, or in my field, speech multilingual models, so one model that can recognize hundreds of languages within one model. These models are very impressive, but because they're so large, they're very computationally expensive. And in a research context, we often just don't have the resources that these big companies have. So wouldn't it be nice if, like Alice here, we had a magic potion that made things smaller? There's a couple of techniques you can use to do this, such as model adaptation, where you insert your own small layers and only train them. Model distillation, where you use a big model to train a small model. Or what I use at the moment, which is model pruning, where you chop out parts of the model that you don't think are going to be useful for training down the line. So here's a graph that I've generated from some experiments I've done. This is taking a big multilingual model that recognizes lots of languages and just testing it on English after removing certain percentages of the model. So on the y-axis, we have error rates. All you need to know is this is basically the inverse of accuracy, so the lower it is, the better. And on the x-axis, we have the percentage of the model we've removed. So 0 at that end means that we haven't touched the model, and 90% means we've taken 90% of the model away. Unsurprisingly, 90% increases the error a lot, so it's much less accurate. But the interesting thing about this graph is that you can remove about 50% of one of these models and barely impact the accuracy at all. That's how big these things are. You can even take it up to about 60 or 70% and still haven't impacted the accuracy that much. So that's a much more computationally efficient model for roughly the same trade-off in accuracy, right? We've also shown in my research so far that you can actually use these techniques to isolate certain pockets of models that deal with certain languages. So for example, I could try and find the English part of a model. And we're hoping, as we go forward, to leverage these parts of the model to actually get better accuracy on certain specific domains. So for example, if we found the English part, we might then train on German, which is another Germanic language. So you'd hope that that would then give you better accuracy. So I'm hoping by the end of my PhD that not only will we have more computationally efficient models, but they will also be more accurate on the domains they're intended for. So that's my presentation. Thank you very much.
Hi, do people have questions? I have a quick question. So you mentioned about model pruning. Do you think you have reduced the initial complexity with the method? What would be your estimate reduction of complexity?
In terms of, how do you mean?
A complexity as in like compute power, for example?
Yeah, so it's a bit complicated because of how the optimizers work. So it's
Yeah.
not just a 50% reduction in compute power, but you're always reducing how much numbers you need to compute basically when you're chopping these out. So it is always going to be more efficient to remove parts of your model basically. And certainly if we can do it to 50%, you're getting a much better trade-off for how much you're spending on compute power versus the accuracy you get at the end.
All right then, thanks.
No problem.
All right, next is Lucy. You're here.
Yep.
So you have the clicker here.
Great.
And around 30 seconds to the 3 minutes, I will just stand up from there.
Okay.
All right.
So manganese 4-X, gallium X nitride, a tale of two sublattices. So the reason why I chose this title is because the material of interest in my PhD is manganese 4-nitride, which is a ferrimagnet with two different manganese sublattices. So ferrimagnets have gained a lot of attraction for use in spintronics applications in recent years because they really combine the advantages of both antiferromagnets and ferromagnets. So like an antiferromagnet, they've got two different sublattices which are anti-aligned, but like a ferromagnet, the system actually has a net magnetization because these two different sublattices have unequal magnitudes, so they don't entirely cancel each other out. And the thing about ferrimagnets is that some of them have very interesting magnetization versus temperature curves. So if you look at this graph here, you can have a point, a temperature, below the Curie temperature of the system where the magnetization actually goes to zero. And this happens if the rate of change of the magnetization with temperature of the dominant sublattice, which I've called A here, is greater than that of the other sublattice. So by increasing the temperature, you can come to a point where the two actually have equal sublattice moments. So this is very interesting for spintronics applications. Because close to compensation, ferrimagnets actually exhibit very fast spin dynamics like an antiferromagnet, but again, they can still be manipulated and detected by an externally applied magnetic field. So manganese 4-nitride is a ferrimagnet, but it doesn't actually have a compensation temperature. So there's no temperature below this Curie point of the system where the magnetization is zero. However, if you dope it with non-magnetic elements, such as gallium, which replace manganese at these A sublattice sites, you can actually introduce a compensation point. And it was shown in bulk manganese 4-nitride that room temperature compensation was possible by doping with a certain amount of gallium. This X value equals 0.26. So then we asked ourselves the question, can we achieve compensation in gallium-doped manganese 4-nitride thin films? And if so, how do their properties actually differ from the bulk material? So I grew a series of gallium-doped manganese 4-nitride on substrates of MgO, and I measured their magnetization, their magnetic properties. So here I'm just showing a plot of the magnetization versus gallium content. And what you can see is that firstly, with increasing gallium content, up to a value of about X equals 0.18, the magnetization decreases. You hit a point where it's about zero, and then it starts to increase again. So what this tells us is that we have indeed reached room temperature compensation in gallium-doped manganese 4-nitride. What we actually also found is that less gallium doping is needed in the thin films in comparison to the bulk material. And this is just related to the fact that the net moment of thin film manganese 4-nitride is lower than that of the bulk. So I hope I've convinced you that manganese 4 nitride doped with gallium is a potential material for applications in ferromagnetic spintronics. Thank you.
People have questions?
Where would this, where would this be applied?
Similar to what Brian said earlier, for magnetic storage, yeah. So our group, we're really working on potential new materials. It's sort of a fundamental project. No major application in mind right now, but just looking at the properties and seeing how we could use this in the future.
So would it be increasing the density of storage, or is it?
Yes, yeah.
So I have follow-up questions. Like lately, I'm not much into storage, but I'm thinking that is other storage moving away from magnetic storage and moving to solid state drive?
Yeah.
Well, because I'm in a magnetism group, I like to really think about using magnetic materials. So for me, hopefully not. Yeah.
All right, thanks.
Okay.
Next is Amir. Yes. You have the clicker here. You can just try. Yeah. Okay. And probably for 30 seconds, I'll just stand up from there.
Hello, everyone. My research is about speech perception and how the brain processes word meaning. Now, in order to do that, we actually record the neural activity of the brain while listening to speech. Doing so, it has been shown that the brain works in a predictive manner, meaning that it consistently builds prediction on upcoming words based on previous context. For example, if you look at these two sentences, I drink coffee with socks and I drink coffee with sugar, and if you compare the neural activity of these two sentences in a speech task, you can see that there is a significant difference, around 400 milliseconds in the neural activity after the onset of each word, with the unexpected word having a stronger negativity. But these approaches have been applied to very constrained scenarios with isolated sentences and unusual words like these ones. We want to see what actually happens in natural speech. In doing so, we modeled the brain as a linear time invariant system, where we have a certain input and a certain output, and we want to estimate the impulse response function of this model. And because we are interested in how surprising a word is and how unexpected it is, we use a feature called lexical surprise, which basically quantifies how surprising a word is based on its previous context. Now, in order to evaluate how our model performs or how good it is, there are two ways that we can do that. After fitting the model and estimating these impulse responses, or what we call TRF weights, we can actually estimate the output given a new input and compare it to the actual recorded neural activity. Or we can basically look at the TRF weights. In both scenarios, we compare these our results with a null model, which is basically doing the same thing that we do over here, but on features that are irrelevant, meaning that we assign random values to each word, meaning that they're not exactly the same thing. So we kind of shuffle the values. When applying this to lexical surprise and seeing how lexical surprise is encoded in the neural activity of the brain, we can see that the differences, although existent, are very, very small. So in the weights and also in the prediction correlations. Now, this is very problematic if we want to compare two models that are very similar, or even comparing cohorts to see if, for example, autism or ADHD participants process lexical prediction in the same way or in different ways. Now, the one solution that we have is that if as I said in slide number 1, the effect mainly happens around 400 milliseconds after the onset of each word. So basically, by chopping off these predictions and correlating these values with the actual recorded EEG, we can get a double increase in effect size, which then in future can very much help us to disentangle between different models and also applying it to different cohorts, for example, as I said, autism and ADHD, and seeing how they process lexical predictions. And that's it. Thank you very much.
Two people have questions.
Just, thank you. I suppose I'm just curious about the 400 milliseconds mark. Is that consistent across groups, or would you expect that to change?
Well, we expect to see a delay between different cohorts. For example, literature shows that, for example, ADHD has a delay in that 400 milliseconds. But again, if we use the same approach in natural speech, we will see that in the impulse response function or the TRF bits that we see, that we have.
Would this apply to non-natural speakers as well?
Non-natural speakers.
As in, if, for example, English is not my native language.
Oh yes. Oh yes, we actually have studies done on that as well. Yes, we can use the same approach on if it's your non-native speakers. There's no problem. We can use the same approach.
All right, thanks. Is there more questions? If there's not, all right. Next, we have Luca. This is the clicker. You can just try forward, backward. And by 30 seconds, I will try to raise the pen this time. For standing doesn't work. People don't see me.
Okay. Perfect. Okay, the rare earth elements are a group of 17 chemical elements that are of great importance in today's world. They have a wide range of application, technological and green energy application. Even if you don't know specifically their name, probably if you have a phone in your pocket or a laptop in your bag, you are relying on these elements. They're used in very big quantities for the production of wind turbines, solar panels, and even for technological devices like your smartphones. The very big problem with these elements is that the geological origin of their or deposit is still uncertain and under debate. And the current techniques that are used for the extractions are often inefficient, costly, and very harmful for the environment. Luckily, geochemistry and mineralogy can give us the tool to try to solve this problem out. How? It is possible today for us to try to reproduce in our laboratories the crystallization processes of the rare earth bearing minerals. How is this possible? The idea is quite easy. It's like if you want to prepare a cocktail, you have to start with the two chemical solutions. You have to mix them, okay, shake a little bit. You leave them reacting under different pressures and temperature for a while, let's say, and then you can get your solid sample. The idea is quite easy. The realization sometimes is not, trust me. Then, when you got your solid sample, your synthetic mineral, to gain a deeper knowledge about its chemical properties, we use different spectroscopic techniques of analysis. One of the most important is the X-ray powder diffraction that is indispensable for the crystal identification. So we can know, for example, at every stage of our crystallization reaction, which mineral is we are synthesizing and if it is stable or if it's transforming in some other minerals. Then it is important even for the quantification. So we can reconstruct curves like this that are the crystallization curves step by step to know the kinetics of the reaction. Another powerful tool is the scanning electron microscope that, as you can see here on the right, can give us very, very nice images and very satisfactory results, and are important for studying the morphology of our synthetic minerals and for elemental microanalysis to see how the elements are spread on the surface of the crystals. Combining all these results together, what we can get? We can get a very deep knowledge at atomic and nanoscale of our minerals, our rare earth elements minerals. Then this knowledge, studying again, we can apply it for trying to shed light on the geological origin of the ore deposits of these rare earth minerals. And then, studying deep the properties of the specific minerals, what we can get? We can try in future to develop new and clean techniques for the extraction of these elements from their ore. Thank you.
People have questions?
Yes.
I suppose I'm just curious on the SEM images there. For the minerals that you're making, do they tend to be in powder form or are they?
We have powders. We get powders, and then they are nanometric powder, nanometric to micrometric powders.
It's just they look so different between them. It's impressive.
Yeah. These are, for example, some micrometers. I think this, for a scale, should be 2, like this, 2 micrometers. Yeah.
So it is not applicable for recycle, right?
Okay, recycle is another thing, but one thing that we can do and that we are trying to study is to use common minerals like this. Okay, this is calcite, it's a common carbonate minerals, to try to get these rare earth elements from the wastewaters from the minings. It's not recycling, but it's try to, let's say, to catch them from wastewater. So water is waste. So it's a sort of recycling, let's say.
Yeah, I have last question. Do you know how much time does it take typically for the process?
For the crystallization process?
Yeah.
It depends. It depends on temperature, on pressure. You can have minerals that you synthesize in a couple of minutes. Like, okay, common mineral like calcite, you can take 10 minutes to have it.
Okay.
For these minerals that are rare earth elements mineral, you need high temperature, and usually, okay, let's say this can take 2 months. This other we got in 1 week, more or less.
Okay. All right. Thanks.
Thank you.
Next we have Y. Is that how I say your name?
Yep.
All right. Okay, so here's your clicker. By 30 seconds I will raise my pen.
Do I click?
Good point. So you do this, it goes forward. You do this, it goes backward.
So our biological clock is controlling our bodily function following a 24-hour cycle. And as the sun is the regular thing that rises and sets every day, it has been the thing that regulates our biological clock, which is light. However, being indoors for the long periods of time, and with the invention of light, artificial lighting, our daily light has been very monotonous, same brightness, same color throughout the day. However, you see the sun, it will be dim, and it will go into very bright in the daytime, and especially it looks more blue. And our biological clock has been adapted to the sun brightness, and so our biological clock as well is more sensitive to the blue spectrum of light. As you can see, the sky is blue as well. So then, with the invention of artificial lighting and being indoors, a lot of us tend to have misaligned circadian rhythm or biological clock, which causes us to have some health issues like insomnia, depression and such. And so one way of doing things is to mimic the sun. So a lot of companies have tried to use artificial lighting that changes the light, the brightness, and even the color of the light. But the way that I'm approaching in my project is to use the sun itself. And this is a concept called daylighting, which is using the sunlight, natural light, in the indoor spaces. So the easiest way is to use windows. However, that is not efficient when you have a very large building size. So one way to do that is to use light shelves. So for example, what my project is using is a curved reflector, which will concentrate the light into a small aperture, and that can channel the light using reflective surfaces deep into the building interior. In this way, what we can achieve is that we provide sufficient light deep into the building, as well as not using any artificial lighting, saving energy as well. So is this light sufficient then for synchronizing our biological clock so that we can have a healthier indoor environment? To make sure that we have that sufficient light, we can use luminescent materials which absorbs light and emits light in a different color. And using this method, we can shift the spectrum to bluer color and thus ensure that we have sufficient light for our biological clock. And therefore, daylighting could be a solution for sustainability as well as our health. Thank you.
People have questions? This one.
Sorry. So you may not be changing the time or you change the light. The time in the day you have the light in the house or you change.
Yep, so because the sun will change in position and brightness as well as the color of the color through the sky, the light that enters the house will change throughout the day, and so that will actually happen as well. So it actually creates a more dynamic indoor environment as well.
Have more questions?
So to capture the light as the sun moves, do you not need mirrors which move around as well?
So there are active ways of tracking the sun, but the thing is that would require energy input as well and a lot of computational work. So there are some methods of using a static concentrator. So in this case, we would actually simulate the system so that we determine what is the best angles and the best configuration orientation, and that would maximize the amount of light captured throughout the day. And so that's kind of the project that I'm working on.
All right, thanks. Next we have Sara.
That's me. Yeah, that's me.
All right, that's you. Yeah. So there's a clicker, and by 30 seconds, you can try
this
yeah.
one? Yeah, okay.
I'll raise my pen at 30 seconds.
Okay. Hi, everyone. So the gray guy is Joe, and he's at a party in a room that is very noisy, and he's trying to talk to Aoife, the green girl. He's very interested in what she's saying, but he can barely hear her because of the noise, and also because the orange girl, that is Laura in the back, is talking loudly to another person. And in auditory neuroscience, this scenario that is very familiar to many of you is called the cocktail party problem. And in auditory neuroscience, it is also well established by now that we can decode Joe's focus of attention from his brain activity alone. So this means that if we have Joe's brain activity, and if we have a recording of what Aoife and Laura are saying, we can determine who he is paying attention to. And pay attention, he's hearing both of them, but we can select who is willingly paying attention to. This is very important. So how do we do it? Well, the way we do it is we build simple linear models based on lagged linear regression to correlate Joe's brain activity to speech features of both of the speakers in this scenario. And then we can establish who of the two is the attended one. But actually, if you think about it in realistic listening scenarios, it is very unlikely that I want to listen to one person for a long time because I get bored or I get distracted. So a more representative description of the scene is something like this, where let's say at midnight 25, Joe is paying attention to Aoife, he's very focused on her, interested. So he's representing all the speech features of what she's saying. So from the acoustics, so the ups and downs of her voice, to the semantics, so the way that words are combined and bring meaning to what she's saying. But at some point, let's say midnight 28, he gets really bored, and so he decides to switch attention to Laura in the back, but pretending to listen to Aoife, but actually his brain has switched. So what he performed is an attention switching. And this context, the cocktail party scenario, so the fact that the brain is able to sustain attention on one speaker, but also the fact that the brain at some point is able to switch attention, is the focus of my PhD project. And what we were able to observe up until now is something like this, where you see on the y-axis the brain speech encoding, so how well a certain speaker is represented in the brain. And you see that the green line is Aoife in this case, and after the decision of switching has been made, very fast Aoife's encoding drops, and Laura's encoding from behind him goes up at the same time, more or less. And there is an intersection point that it would be the neural attention switching. And this is very important both for understanding how speech works in the brain in general, and also for applications such as designing new hearing aid devices that could be steered by the listener's attention. So thank you. Yeah. I don't know how to, yeah. Right.
Do we have questions?
Thank you.
How would you decide between conscious versus unconscious switches?
Well,
be a technical question. Sorry.
I mean, I think, well, what do you mean, conscious or unconscious?
So you could, in theory, also switch because it's a cocktail party.
Yeah, I mean, it's hard to say what it means to pay attention, because sometimes, let's say you're listening to Aoife, but she's quiet for a moment. Mm-hmm. Then I think your brain unconsciously is kind of actually listening to the other conversation, and maybe you don't realize. And this has actually been shown using intracranial data. So sometimes when people have epilepsy, they put electrodes inside their brains. And so they were able to see that when the attended speaker is kind of silent, you're actually unconsciously switching to the other one. So yeah, there is a slight difference, but maybe we don't realize. Yeah.
Last call for questions. Yes.
So access of the brain speech encoding is only get from the brain signal and the speech.
It's basically how well you can decode a certain speech feature using the EEG. So you're basically reconstructing, let's say, the envelope of the speaker, so the envelope of the voice, and a model that is trained well, so it represents what's going on in the brain, will be able to reconstruct in a good way, and a model that is not won't do that. So basically, that's what it's a reconstruction correlation. Yeah.
All right, that's it. All right, thanks again. Here, last speaker for the day, that's Mohsen. So there's a clicker, and by 30 seconds I'll raise my hand. Yeah.
Okay, my name is Mohsen, and I'm working on wireless communication, especially on technologies beyond 5G. When we talk about 5G and 6G, you may be familiar with this kind of things with higher speed or lower latency. But for us, these kind of generations are a kind of predefined requirements and a set of technologies to meet this kind of requirements. But my work mostly focuses on these two requirements: user experience data rate and speed. For example, in 5G, we can provide 100 megabit per second at the speed of 500 kilometers per hour. But already today we have some kind of vehicles such as these airplanes or bullet train. The speed of this kind of vehicles are higher than 500 kilometers per hour, and that's the task for 6G to provide internet in a speed of 1,000 kilometers per hour. And here we have the architecture. A passenger here use the services like gaming, streaming, or something like this through this channel, through this architecture. And the most serious challenge in this architecture is time-varying channel. But what happened in this time-varying channel is something like this. We have a signal, and we have attenuation, delay spread, Doppler spread, noise, RF impairments, and whatever these kind of challenges. And here we are looking for solutions to address these kind of challenges. And there are multiple antenna technologies, some beamforming techniques, and waveforms. And I focus on waveforms. For waveforms, we have OFDM and OTFS, and OTFS for 6G, it's maybe for 6G, and I'm working on OTFS. It has been recently introduced in this area, but it's very good in the theory, but its practical aspects is in their infancy, so I focus on the practical aspects of OTFS by pulse shaping and synchronization. For pulse shaping here, I try to save this guy by putting some shield or something like that. For synchronization, we try to estimate the time this guy arrives home, if he arrives actually. And by using the features of these bad guys here, delay spread, Doppler spread, actually I designed a 2D window, a sliding 2D window to find the periodicity or diversity of this spread, delay, and Doppler spread. And that's what we propose here for this kind of waveform. Thank you.
Do we have questions for these fancy graphs?
No question. It's a very big question, actually. Thank you.
All right, thanks.
Thank you very much for coming, everyone. I'm Declan O'Loughlin, the Student Branch Counsellor for the IEEE branch, and myself and Vibhuti will present the prizes. We have 3 prizes. There's a first place and a second place chosen by our judges, and then the audience prize winner chosen by yourselves. So I'm going to announce second place first of all. So that was Luca Terribili. So if you want to come up and join us. You stand in the middle then. Vibhuti, you come over there to me as well. You stand in there beside me. Sure. Yeah. Congratulations.
Thank you.
And next, our audience prize winner, who was Sara Carta.
Congratulations. If you stand in there between the two of us.
Yep, sure. Wait, sorry. Wait. Okay.
All good. Thank you. And finally, our first prize winner, who was Y Quan Tham. Congratulations. That marks the end of our Threesis for this year. So thank you all for coming. We might thank our speakers and congratulate our winners once again.